Okay, so we have an exam. Who's invited? My people, okay? So where's the material start for the test?
Right
All
out.
the Bohr-Atom stuff. What do you think your chances of getting some Bohr-Atom questions are?
100%.
Yeah, I think it's probably up around there. Yeah, I think that's, you might want to.
102%,
Yeah,
2%.
yeah, I think there's a good chance of that. Then it goes up to basically, what I described with a metal and insulator and a semiconductor as well. So you should be able to draw that little diagram and talk about filling up the energy levels and the gap and stuff like that. And that's where the material starts. We're doing the 3D stuff now. That'll be on the third test. The other thing is, because it does affect you. I don't know how it's going to affect you entirely yet, but there was a meeting called the GOMD meeting, Glass and Optical Materials Division of that I've gone to before, and I was asked to chair a session of it. I said yes. It's my own fault. I did not look at the time of the meeting because it has always been mid-May, end of May. So I just assumed it was the same time. It turns out this meeting is during finals week. And so turns out I don't know quite what to do yet. Most likely, you'll have an exam and whatnot, but most likely you're going to have somebody else proctoring the exam. And so that's really messing up everything in my life right now. So I'm trying to figure out how to get everything, what the implications of that will be. I don't know yet. I'll let you know when I figure it out myself. And then the other thing, we'll keep on having more of these extra classes to kind of make up for everything and stuff like that. Okay. And we'll see how well the times I picked work. Maybe they have to be modified. I don't know. Okay. So that said, we're looking at, we're going to look at the 3D Schrodinger equation. This, and we started off with this guy here. And what did we do? We assumed
Product
a product solution. And this is the function of x, y, and z, and t. The product solution is a product of what two functions?
position and time.
Yeah, so we just called regularly psi or a function of x, y, z, just a function of position. And then we have this time t of t. We put this all in there, we beat on it, and what did this end up with? The result was we ended up with this guy here. But this E here is the eigenvalue. Psi here is your eigenfunction. And then the T equation is going to be this guy here. That's what we had last time. Well, we solved this before, so this is from before. We know that this equals this expression here. This is e to the minus I et over h bar. This is from before. And since you've been studying for your test, you probably remember seeing that derivation in your notes. Okay. So what we want to do today is beat on this guy here, and this will also be a good review for your test as well. And so we're going to take the case where the v is a constant. So let's solve this. The 3D time independent Schrodinger equation. For a 3D finite box. So let's see what this is going to be here. So here's my x, y, z. And draw a box like this. And I'll call this A, call this B, Call that C. And hey, what do you think I can take the potential inside the box to be? 0. I'm gonna say V inside is 0. And then I'm gonna say the V all outside here is gonna be a constant. So this is the 3D version. What's the 3D version of? The 1D box. It's gonna be the 3D version of this. We had a V here like this. We call this L. So that this is V naught here. And this is V naught here. This is X. It's just a 3-dimensional version of that. Okay. So let's proceed. You tell me how to proceed. So we know that we can write the equation like this. And this V is a constant. You have your hint last time, so we know that this psi is a function of x, y, and z.
We do the same thing we did last time,
Meaning
assuming a product solution,
of,
X, Y, and Z.
yeah, it's just some function of x, some function of y, some function of z. And I'm gonna take variables to basically that kind of look like those letters. So I have a chi here. Chi looks close enough to an x. I have a fancy y here, and that looks close enough to y. Then I have a fancy z here, and this is gonna be a function of z. Okay. So again, this is a product solution. Mathematically, when you have these boundaries and stuff like this, and there's boundary conditions, you call this a boundary value problem. And it turns out you use these product solutions all the time in these boundary value problems. So when you take, you're all in the, have you done this yet, your math course yet? You'll probably do it toward the end. If not, turns out you're gonna be seeing it in, let's see where else. When you take the E&M course, you don't do anything without this. If you take the advanced engineering math course, which probably some of you will, if not all, both of you, you're going to see it all the time. Okay, but this is one of those top 4 math techniques. Okay, what do we always do with this? We always take the solution and substitute it back into these. Okay. So before I do that, I'm going to clean this up a little bit. Okay. To clean this up a little bit here, what I'm going to do is I'm going to take the V over here and I'm multiply it by this guy here. So I'm going to, so first, let's, you know. So I'm going to take the V to the other side. So this would be this E minus V. Here. And then I'm going to multiply by the reciprocal of this guy here. And this would be all the other terms. And what do we know about this term here? It is a
Constant.
constant. And I'm gonna have two ways of writing that constant depending upon V. Hey, what do you think the two situations are gonna be? When E is
bigger and smaller.
bigger than V and E is less than V. So we have two cases. So like before. We have two cases. E is greater than V. And E is less than V. This would be good review for your test as well. Okay, which one, what do we do if we have the E greater than V?
Zero.
Okay, V is gonna be zero, we're gonna, I'm gonna leave it like this for all, what you said is correct.
Yeah.
We always had the V equals zero case. Well, let's just say it's just this and it's not zero yet, it's gonna be. So is this part here, the, E minus V, is that positive or negative?
Positive.
Positive. So this whole thing here is a positive, and then you have a minus sign here. So what we do, we define something called k squared. It's gonna be this two m h bar squared e minus v. Now, the whole, in the 1D case, we take the v to be zero here, but in general, we could have this. So in this case, our equation becomes what? The equation becomes this guy here. This is just showing it. What happens if you're the other case? Then what do you know about 3 minus v? This is gonna be negative. I get another negative, so the whole thing is positive. So what we do here, is we call this whole thing here. Since this is negative here, I'm gonna multiply through with a minus. What do we define that as to be? That's our definition of. Yeah, okay. This range it was the beta squared. This is your beta squared. Okay. So this equation then becomes this guy here. Okay. So in other words, when I write this, I can have this being either minus k squared or beta squared times psi. I can have one of those things like that. The main thing is that this is a constant. Make sense? So let's go through and do it. I'm going to do the minus k squared because that's going to be the one we're going to use in the most. So let's go through and do it. So look at. Look at this. So we're going to assume the psi is this chi, y, and z. And I'm going to write it like this because it's a lot easier than putting down the functional dependence. Since I think in this form here, the functional dependence is obvious. Okay, so let's see what we have here. So I'll put this all in here. So this term gives me this. This. One. Okay, you tell me the next step. What can I do with this string here?
You take out the constant,
If you tell me what you mean, because I don't see any constants there.
the y and z
Do not depend on,
x
so therefore
come on.
they come on that partial. Okay. Hey, we have another term. What about that one? This one is then gonna be the fancy X and the fancy Z. And this one is gonna be the fancy X and the fancy Y. Now what? What's the next step whenever you do this? Divide by our original guess. So we're gonna divide everything through by our psi, which is X, Y, Z. And that'll always be the case. We're gonna hit this whole thing here. Divide both sides by the original guess. Hey, what happens over here?
The two cancel.
So this gives 1 over chi. Or fancy X. And this one I get the 1 over y, or should say 1, fancy y. And then 1 over fancies. This side here is a constant. Do you happen to know anything about X, anything about Y, and anything about Z? They are all. What would a mathematician know those variables?
Independent.
They're independent variables. So this term here. This term here only depends on
X.
X. Well, this only depends on X. Which is an independent variable. This term here only depends on Y. Which is an independent variable. And this term here only depends on Z. Which is an independent variable. So when can an independent variable in X plus an independent variable Y plus an independent variable Z always equal exactly the same constant? There's only one way to have that happen. We didn't know about each of those individual terms.
They have to be constants.
They have to be constants themselves. So what this means here is that this term here has to be a constant. I'll call this Cx. This term here has to be a constant. I'll call this one here Cy. And this term here has to be another constant equals C0. So I've taken this equation and I've now factored it into 3 separate equations. I have this equation. This equation. And then this equation. Let's see if I can talk and still do that better. Very small. Does that fit? Yes, it does. And this goes to here. And this goes to here. What are all those equations called, each one of them? They are all examples of
Functions, eigenfunction value system.
Exactly. For eigenfunction, eigenvalue problems. Now we have 3 of them. So why do we call this separation of variables? Because our big differential equation, our big partial differential equation is now factored into 3 separate terms. Okay. And you're going to see this. This is one of these things. Absolutely understand that perfectly because you're going to see this like 8,000 times in your education. And this is one of these major sledgehammers. This is a turning point in your education. Okay. Now what I'm gonna do is I'm just gonna solve one of those because the others are gonna be the exact same. So let's solve one of these. And that one we're gonna solve is gonna be X. Well, let me do one other thing here. If I solve this for the beta equation, what do you think would happen if I had the beta equation? Instead, if I did the case where E is less than B. They have the exact same equations here, but with they wouldn't equal the minus k squared, they would equal
Beta squared.
the positive beta squared. Okay, but I have the exact same thing occurring here. Okay, in which case I'd probably call them a different constant. I might call them like bx, by, and bz. Now, let's look at this. So let's look at next. So I have this. Okay, so what I'm going to do is I'm going to leave this point as a homework problem, which means I have to write it out. What you're going to show in homework is that that constant there actually has to be negative. That's not one bit obvious. It turns out it won't satisfy the boundary conditions. So you will see. Cx must be negative. Okay. So I'm going to define Cx to be minus a constant. And what do you think I might call that constant? I'm going to call it kx squared, minus kx squared. The kx here is going to be positive. I wonder why we're going to have a square there. I can't wait to find out. Hey, what do you think then the CY is going to become? Minus ky squared. And then this one here is going to be then minus kz squared. So I should say likewise. CY will be this guy. And this will be this guy. Okay. So if I put them all together, what is it here? Remember what we had, remember the equation we had. Recall we had. And this, and then the y term, and then the z term, and this is this minus k squared. We call this cx. Now this one here cy. Call this one here cz. So what would this become now? This would really become minus kx squared. Minus ky squared. Minus kz squared. Equals minus k squared. Make life nice. I'll kill all the minus signs, so this is going to give us this. I have to remember we have that. I'll put this over in the corner over here. So we're going to need it. Okay, sure. I have to talk to you anyways, because there's a lot of things I don't know how to fill out.
Okay,
Okay.
yeah,
Okay.
could you send me, the main thing is, could you send me like your full name, date of birth and passport number? whenever you-
No, that's the problem, is that my passport is coming, because it has a little thing that says it has not come yet.
Okay,
And so I do not have it yet.
if you give me the other two, we'll be okay.
Okay, sure. Okay, great.
You'll just have to fill out your passport number then at the airport.
Okay. Okay. The one time you really want government not to be efficient. I could have really been happy if they said, well, we have to reject your passport, we can't get it till August, and all my problems would be solved, but it turns out they were efficient, and I'm getting my passport in time. So let's go through and write this down here. So now we have this equation here. Hey, and the rumor is you two are taking an exam tomorrow. And you might get something like this on here. So you tell me exactly how you solve something like this. I heard you two are pros at this.
You use the E to the PX transformation process?
Exactly. So we're gonna assume, we're gonna assume. And our big X here is this E to the PX. Okay, if I take this, if I take two derivatives, I get this P squared E to the PX. And I get this guy here. They cancel. So tell me what P is.
Just wait.
Minus KX.
Okay, so we have this, P squared is this. P is plus or minus I KX. Hey, why did we take this B squared? When we took the constant, remember we said this constant, let's define it to be minus KX squared. Hey, why did we square this? Entirely here to get rid of it. So usually if you have some weird constant that comes in squared, you wonder why are we calling it squared? It's probably called squared so that in the end you don't have the squared anymore. Okay, so that gives us this. So we have two solutions here. I can have actually the plus IKX or the minus IKX. So if I write this down, I can say that my chi here is going to be some A e to the IKX x, B e to the minus I kx x. Or I think we had another friendly way to write this. What's another friendly way to write this? Now, if you have an e to the I something, what do you think of?
Sines and cosines.
Hey, what's that relationship called? So the knee.
Euler.
Euler, yeah, exactly. It would be the Euler relation. So I put the Euler relationship in here and here, and I collect all the sines and cosines. So another way I can write this is I can say that this is going to be some, C sine xx, some D cosine. And this is the form we're going to use this for. Okay. Go ahead.
Is there an I in there somewhere?
I can absorb that onto the constant. Just call it constant. Okay. So there's that one here. Boom. Hey, what do you think is going to happen to the big Y and the big Z here?
Exact same thing.
The exact same thing. The only difference will be we'll have for the Y, okay, we'll have a KYY, KYY, and then we'll have different constants. And the Z, new constants, KZZ, KZZ. Okay. So we have that. Now let's look at the other case of our chi. So we also have, look at the V greater than E range. Let's keep it the same. That gave us this. We have the exact same equation, but we had this beta squared. Well, we'd have some new constant, 6, 5 like that. On this case here, this CX here, this CX is positive. I'm gonna let this CX here. I define this to be positive beta x squared. That's what that one gives us. This, right? Gives us the. Hey, how many want to solve that? I think that's a great thing to do, okay? So this is gonna be, I'm gonna assume. E to the px. So this gives me p squared e to the px. Equals beta x squared. E to the px. And tell me what p equals.
Plus or minus, yeah.
Plus or minus beta x. So this one in this range, I'm gonna get this chi, it's gonna be some new constant, let's say f e to the beta x. Plus g e to the minus beta x. Okay. Let's look at our little picture here again. Do we have any boundary conditions that have to be met? Yeah, what are the boundary conditions we have on psi?
They have to be equal.
Yeah, we know that psi 1 has to equal psi 2 at some boundary. Okay, so let's actually write this down. So recall the boundary conditions on psi. So I have this psi here, I have this psi inside, and I have psi outside. Okay. Which here's our psi inside the box, and which one here's our psi outside the box?
When the potential is less than E, then it is outside of the box.
The potential is less than E, is outside the box. Mhm. Go back to the 1D case.
The potential is less here.
If your potential is less, you're inside the box. If it's greater than you're outside the box. Okay, so which one would be outside, which one would be inside?
The first one we did is inside.
This is gonna be inside. And this is gonna be outside. So we know that these are functions of x, y, and z. And what did we say about these right here? Okay, we're looking at the x direction here. So how would I write this mathematically? So let's go through and draw a little box here then. So here's your little box. So that this is A, this is B, and this is C. Okay. So let's just look at the x boundary condition. So outside the box would be out here, or kind of on the back side here. Okay, so if I look at this. If I look at just the x-axis, you know, like this in our box. This is 0. This is A. This is inside it. This is outside. What would this give me? How do I write this condition here? Let's give these. Oh, it's forced to erase them. I'll call this one I for inside, and then I'll call the other one. I'll just call it 2. Our other one was this. Here we have what, F and G? So how do I write this condition here?
Say. Chi1 of 0 has to equal Chi2 of 0.
This is chi1 0, this chi2 of 0. And what we have on this side here?
Same thing, but with n.
And the chi1 and then mixed with this chi2. Okay. We'd really have another, we'd have like a side 3 with different coefficients, but we're gonna, I'll be a little sloppy here. Okay, does that make sense? Now, what else do we have? What are the other boundary conditions? The wave functions have to be the same, but what else has to be the same?
Their derivatives.
Their derivatives. Okay. So the other one I'd write is what? What would be the corresponding other boundary conditions? These are why these are called boundary value problems, because of these boundary conditions. Okay, let's just pretend maybe you have an exam on this. Let's say it's Thursday, for no good reason, meaning tomorrow. Okay. And the beginnings of quantum mechanics. And maybe there's a problem with two wave functions. With a boundary between the two. Okay. What would you write for this one then?
Just the derivative of Chi1
1
with respect
and
to
x, and then what we have to do to this,
evaluate it at
evaluate it at 0. Okay. And this will then have to be this value here. Evaluate it at 0. Okay. And likewise for this one over here. You have them better. And then this one here. Okay. Now, what kind of, when we had that 1D well, we did something to it. What did we do to our little friend, the 1D well? First of all, let's look at here. If I'm on this side over here, okay, what's my wave function? And if I'm on this side of the well, there's a problem with my chi2 here. What was the problem?
oh when x goes to infinity, chi goes
Beta is positive here. I should have beta x. I'm sorry. I don't have a license. When the beta x is positive, so when x goes off to infinity, this term blows up. So what does that mean about the f? This f had to be
0.
0. So on this side over here, this side over here, our chi would have to be this g e to the minus beta x. Because the f would have to be 0. But what about on this side over here? This is 0. So on this side, what was the problem? If I'm over here, my x is
This is negative.
the negative. So I can go off to negative infinity, and beta x is so positive. So which term is going to have problems here?
The one with the minus.
Yeah, the g here, because the beta x is positive. If x goes off to minus infinity, this term here blows up. So that g has to be 0. Whereas this term here, I have beta x, which is positive. If x goes off to minus infinity, this goes to 0. This is what we do. What happens on this side? My chi then has to be my f e to the beta x. This is my, in this case here, the g. 0. Now, what did we do when we did the 1D problem? We set this all up and that was all nice and we had fun. But then we did something. We took a special case for our 1D well. What did we do with our finite 1D well? little finite one D well went through a little growth spurt. It went through puberty. What happened to it? It was no longer the finite one D well. It became the
Infinite.
infinite one D well. So we took our V naught, we set it off to 0. So let's look at. Let's look at the infinite 3D box. So in the infinite 3D box, if here's our box, we're going to take V to be 0 inside, and what's V going to be on the outside? Infinity.
Oh,
Okay. It is really just a three-dimensional generalization. So you're going to say the potential energy outside here is infinity. We have this tiny little box. If we're in there, there's no potential. Okay, so what happens in this case here? So as V goes to infinity, what happens to my buddy beta x? What do you think is going to happen?
We'll also go to infinity.
Yeah, this beta x here is also going to go to infinity here. And so what's going to happen to my wave function over here and the wave function over here? If this beta x goes off to infinity, what does z to the minus infinity? 0. The x values here are all negative. Okay. So if this x is even slightly negative, which it has to be because it's over here. And if this beta x goes off to infinity, what's the wave function there?
0.
0. So what's going to happen here is that when we do this problem here, this is A, this is X, this is my 0. If this V over here is infinity, that means my wave function has to be 0 here at those points. That makes sense? Just like what we had in the 1D well. You two good with that? Ask away.
You say that last thing one more time.
Oh, which last thing?
Like when the chi is going to 0.
Okay, so let's go back and look at that. Remember when we did the case over, okay, the 1D well. We have this guy here. This is V naught, this is L, this is our 0, and this is our big naught. So we know that over here, when we looked at this, the wave function on this side here, I think we call this side 3, was just some constant, I'll just call it C, e to the minus beta x. Okay. And this beta guy, okay, so if this V goes off to infinity, what happens to beta?
It also goes to infinity.
Yeah, so as your V goes to infinity, your beta goes to infinity. Okay. So what happens here? Beta goes off to infinity, x is positive. What does this go to? 0. So my side 2, and then side 3 here, that goes off to 0. Whereas over here, we had a side 1. We have something like this. In this region over here. So in this region here, as V goes off to infinity, again, beta goes off to infinity, your x here is negative. So what does this have to go off to?
Also 0.
0. So my side 1 has to go to 0. So my wave function at those boundaries have to be that. That makes sense? It's the same argument. Again, why do my wave functions have to be the same here at 0 there? Because psi is continuous. Okay, so we have to fix those 2 points. That makes sense? Okay. Let me get one more point, and then we will We'll be in good shape. Okay, so let's apply this here. So apply. The boundary conditions. At x equals 0. And x equals a. To chi. And chi inside the box. So I have chi. Inside the box at 0 would be 0. Okay, what does that give me? C sine 0 plus C cosine of 0. Sine of 0 is
0.
cosine of 0 is okay. This gives me D. So what does it mean about D?
0.
That's me 0. So that tells me that my chi1 or chi inside the box, this is C sine pxx. This might be a 0. Okay. Now let's do the next boundary condition. I think we're going to see something similar. You know that if for A, this has equals 0. I told you this would be good to go for the exam. What is the sine 0? At
At 0
or
and pi.
or
2 pi.
or
3 pi.
integer pi. Okay. So what I can say is that this kxa has to equal nx. It's nx is an integer. And this nx is going to be 1, 2, like this, times pi. So my kx is going to be nx pi over a. Hey, what would happen if we did the same thing for y? Yeah, so likewise, it's y, I can get ky equals, okay, so we could have a different energy, so what would be a nice energy name for that?
And 1.
Ny. So I have ny pi. And what was the direction, what was the width in the y direction? X was A.
It'll probably be
B, okay? And what do you think then the KZ is gonna be?
NZ pi over C.
NZ pi over C. Hey, what do I know about KX, KY, and KC? Is there any equation I said we might need later on? Sorry, I rewrote it someplace.
The one half right corner.
Hey, the one over here in the phantom zone, okay. But general is not. Okay, this K is gonna be what? This K's are 2m E, because my V is 0 inside the box, H bar squared. My KX is my buddy over here. And KY is my friend here. And my KZ is my buddy over here. Hey, I can solve this for E, and I think I now have a new three-dimensional version of my energy in a three-dimensional infinite box. Boom. So my energy in a 3D box depends on three quantum numbers, nx, and y, and nz. And again, if I didn't have the y dimensions, what would happen? This one would be here. But it had the Z dimension, this would be here, hey, that looks exactly like my 1D result. So if I were to write this down even without doing any work and saying, well, that result generalizes to this, you probably wouldn't have any problem. You'd say, makes sense. Okay, but we want to see explicitly where things come from. Okay, we are going to get a ton of mileage on this in front here. Okay. Done. We got new material and prep and review for the test.
Yeah, perfect.
Actually, good.